So in our last lecture, we studied all about torque, and I defined that torque is actually a multiplication of where you apply the force and what force you have applied. But the vector definition of torque usually contains what you might have seen in your book. It contains torque vector is equals to vector R cross vector F. Now question is, from where this cross product have come. Agreed? Now, as I've already stated earlier, whenever you see a cross product, it means we are generalizing a particular concept. Now, why we are generalizing? Okay, consider the rod again. The length of the rod is R. Now, imagine that you apply a force along this direction. Agreed? You apply force along this direction. Can you tell me what is this direction? This direction is the direction of R vector. Agreed? Because you see R vector in this manner. And what is this direction? This direction is the direction of force. So if the angle between the R vector and the force is theta, then can you please tell me which force is actually creating rotational effect? See, this force has two components. One component in the direction of R, that is F cos theta. Can you tell me F cos theta, do F cos theta has anything to do with rotation? No, because the entire F cos theta is trying to pull the rod away from the center point where it is attached. That is, it tries to push the rod outside away from O, but that doesn't happen because the rod is rigidly fixed. So F cos theta has no use here. The another component that acts directly 90 degree to R is F sin theta. So F sin theta is the main force that actually causes the rotational effect. So in this case, what will be my torque? In this case, my torque will be a multiplication of R and force. So what is the force now? So in this special case, the force now is not F, but it is F sine theta, where theta is the angle between R and F. So this is a special case, and in this special case, RF sine theta actually means R cross F. So you see, just cross product means only one thing. You have taken a special case, and under that special case, all different types of cases they come. So when theta is 90 degree, it means we get torque is equals to RF, and we have already discussed in our last lecture what is torque equals to RF is, what condition or what um, thing the torque equals to RF represents. So that's a different thing. So you see, there is an analogy between translation and 1D, because in translation, the work that force did, I mean, force was the main thing that decided the motion, but in rotation, not only force, but where you apply the force is important. So torque is the main deciding factor for a rotational motion. So more is the torque, more is the rotational motion. Now we all know that with each force, we know that force is written as mass into acceleration. Agreed? So question is it possible to write torque equals to some mass into some acceleration? Is it possible for us? Because as I said earlier, that torque is an analogous quantity to force in 1D. Okay, now the main thing is, can I find an expression in rotation that exactly corresponds to some mass multiplied with some acceleration? So let us see. So consider the rigid body again. Look at this rigid body, okay, which is fixed at a particular end. Say it is fixed at this end. Okay, now if you are applying a force here, okay, then this force will make this object move in circular motion. That you agree? Okay, but can you tell me what type of circular motion? Obviously an accelerated motion. As I've already said, if there is a force in the linear direction, so this is actually the linear force, then this linear force will make the rod move with an acceleration a. A is the linear acceleration. Agreed? So this expression torque can be written as R. What is force? force is mass into acceleration. So what is the acceleration created? That is AL. Agreed. Now you all know that the acceleration AL can be written in terms of angular acceleration. So what is angular acceleration? The rate of change of this angle. Okay, so we all know this thing, that the angular velocity was d theta divided by dt, the rate of change of angle. Now if an object moves with an acceleration, then the angle does not change at a constant rate, but it changes continuously with time. So under the application of force, there is an accelerated motion in theta. So theta changes in a different way. So now under the influence of force, we can write this as d square theta by dt square. Great. And we also learned the relation between linear acceleration and alpha. So linear acceleration was r into r cross alpha. So let me write r alpha. So remember why I'm removing the cross. It's just because that it represents special cases, so it doesn't matter. So if I can write al as r into alpha. Now what does this mean? This means I will be having m sum r square and alpha. So now torque is written as what? M sum r square into alpha. So now the corresponding analogous thing of acceleration is alpha, then this mr square must be something that behaves like the mass. Let me repeat. So the mr square must be something that behaves like the mass. This is called the moment of inertia I. So moment of inertia I is the mass into distance. So in this case, see this case, what is the value of I? This case, please don't say the value of I is mr square. It would be wrong. It would be completely wrong, because when I did this particular derivation is valid for some object that is exactly at a distance r. Okay, and there is a string. So consider this string is negligible mass. So for this thing, this derivation is valid, because I consider mass here. When I have written only mass, I only mean the mass of the thing that is at the edge where the force is getting applied. Okay, I do not consider the complete mass of the thread, since thread is massless. So in this rod, I cannot write just m as mass. Okay, because this force is acting on the entire rod, and somehow I have to find something analogous to mass, but I cannot write mass. Okay, so moment of inertia. So let me repeat again. So if you have a massless thread, and if you have an object that is a ball attached, and you apply a force on this ball, then what happens? The torque experienced by the ball is Rf. Now what is the force on the ball? Force on the ball is F, and this force will create an acceleration in the ball, and this is equals to ma. Okay, see, try to understand. This is a one dimensional formula. Force is equals to mass into acceleration is a one dimensional formula, where the entire force acts on the entire mass. Only then this formula is valid. You cannot write force into acceleration for this case, because the force is not acting on the entire mass. The force is acting somewhere on this part, and as a result of which the all part moves. But that doesn't mean you can write force into acceleration. So when I did this derivation, the main power that I have written force is equals to mass into acceleration, it indirectly represents that I have considered a system that has the entire mass concentrated at the edge where the force is being applied. And then from here I have derived a quantity which is m r square into alpha. Okay, alpha is the angular acceleration, and for this quantity the entire mass is at a distance r. Okay, so this is the moment of inertia I. So moment of inertia is, how moment of inertia is found out? The moment of inertia is found out in this manner. find the place where the entire mass is concentrated and square that value. Agreed? And tell the mass which is concentrated, that is m. In this case, in this particular case, in the case of rod, the entire mass is not concentrated at a particular distance, but it is distributed. So for this case, the moment of inertia is going to be different. So in the next lecture, we'll talk more on the moment of inertia. But for now, let me just tell you as a reminder that torque can be written. So if force is the analogous quantity to torque, and if force can be written as some mass into acceleration thing, then torque can also be written in this way, given that instead of mass we have a quantity which is mass into distance square, that represents the moment of inertia. So the moment of inertia is actually the quantity in the rotational motion that is analogous to the mass in translational motion. Agreed? So remember this. We'll discuss more in the next lecture.